Greetings of the day to all of you. I welcome you all to yet another lecture on power quality problems and solutions. In today's lecture, we are going to solve some three-phase unbalanced systems. Say a three-phase star connected or Y connected system which is feeding an unbalanced load, and then three-phase delta connected system which is also feeding an unbalanced load. Before we go for the compensation of three-phase unbalanced systems for phase balancing, magnitude balancing, and for power factor correction, and for harmonics compensation, we must know how to solve these three-phase systems or three-phase circuits. So let us first of all go for three-phase Y connected or star connected unbalanced loads. Unbalanced load. This is part A. I have a load which is Y connected or star connected. My supply system is also Y connected. My load is also Y connected, but my load is not balanced. It's an unbalanced type of load. Let me draw the circuit diagram. This is the circuit diagram. Let me first of all complete the circuit diagram, and I will explain it. This is phase to neutral voltage or phase voltage VAN. This is phase voltage, the phasor is VBN, and phase C voltage phasor is VCN. The three line currents are line current phasor IA, line current IB, and line current IC. And the three loads which are star connected or Y connected are ZA, ZB, ZC impedances. And ZA is not equal to ZB, not equal to ZC. It's an unbalanced load. The supply neutral is N and the load neutral is small n. And let us assume that two neutrals are not connected for now. In order to solve this, we have to solve this three-phase system, three-phase Y connected supply feeding a three-phase Y connected unbalanced load. We have to find these line currents IA, IB, IC. In order to find these line currents, we will use the mesh current analysis. Let us go for mesh current analysis. Mesh current analysis. You have already studied mesh current analysis in your basic circuit theory. Let us assume this is mesh current I1 and this is mesh current I2. So using KVL, Kirchhoff's voltage law, in this mesh first and then in this mesh. Let us apply KVL in this mesh. We will start from here. Minus VAN, because we are going from negative to positive, and by convention when you move from negative to positive terminal the voltage is to be taken as negative. So minus VN plus this drop plus I1 ZA, then plus drop across this impedance ZB. What is current through this impedance ZB in terms of these mesh currents? This is I1 and this is I2. I1 is in this direction, I2 is in this direction. So it is I1 minus I2. I1 minus I2 ZB. And then plus this voltage. What is this? We are going from positive to negative. We have to take this positive. Plus VBN is equal to 0. Okay. Let us solve it. Minus VAN is here. Let me take this VBN here plus VBN plus I1 ZA plus I1 ZB minus I2 ZB is equal to 0. Okay. Now let me change the sign. Let me multiply the whole equation by minus sign. So this will become plus VAN. This will become minus VBN. This will become minus I1 ZA. This will also become minus I1 ZB, and this will become plus I2 ZB equal to 0. So from this, VAN minus VBN is equal to okay, minus, if I take I1 common, what I get inside is ZA plus ZB plus I2 ZB equal to 0. Okay, the further solution of this equation gives us, so VAN minus VBN is equal to, I will shift these two terms to right hand side. Here it is minus, when it is shifted to right hand side, it will become plus I1 times ZA plus ZB minus, this will become minus I2 times ZB, minus I2 ZB. Let me call this equation as equation 1. Okay, so I have applied KVL in this mesh. Now similarly, let me apply KVL in this mesh and solve this mesh in terms of mesh currents. Okay, by applying KVL in this mesh, I will start from here. So I will get minus VBN, then move in this direction. What is the voltage drop across this load impedance in terms of mesh currents? Mesh current I2 is flowing through it in this direction, but mesh current I1 is flowing in opposite direction. So it will be I2 minus I1. The current through this in terms of mesh currents is I2 minus I1 into ZB. Then plus this drop. What is current through this impedance? It is I2 plus I2 into ZC, and then plus this voltage plus VCN is equal to 0. Okay, so I will write minus VBN. I will take this VCN with this plus VCN, plus I will expand this. I'll open this I2 ZB minus I1 ZB plus I2 ZC equal to 0. So I will again change the sign. This is minus VBN. Let us make it plus VBN. Multiply it by minus sign. So this has become plus. This will become minus VCN. Okay. This let me first of all write this I1 term. So this will become plus I1 ZB. Okay, and then minus I2 ZB, then minus I2 ZC equal to 0. Or I will get VBN minus VCN plus I1 ZB minus, I will take I2 out common. When I take I2 common, minus I2, what I get inside is ZB plus ZC equal to 0. Okay, further simplification gives, on the left hand side I will keep VBN minus VCN equal to, I will shift all these two terms to right hand side. Here it is plus I1 ZB, it will become minus I1 ZB. Here it is minus, when I shift it to right hand side, it will become plus I2 times ZB plus ZC. ZB plus ZC. This is my equation 2. So therefore, in terms of mesh currents, I have two equations. This equation, equation 1 and equation 2. Let me write these two equations in matrix form. In matrix form, let us write equations 1 and 2 in matrix form. So I will get VAN minus VBN. Okay, and then second term is this VBN minus VCN. VN minus VBN from equation 1, and from equation 2 VBN minus VCN. Okay, so this is equal to impedance matrix. What is impedance matrix? What is the coefficient of I1 here? It is ZA plus ZB. It is ZA plus ZB. What is the coefficient of I2 here? It is minus ZB. Okay. And similarly, coefficient of I1 here is minus ZB, and coefficient of I2 is ZB plus ZC into I1 and I2. Here it is I1, here it is I2. So this is in matrix form. Now what is the aim? Aim is to find the mesh currents I1 and I2, because once we know mesh currents, we can find these line currents IA, IB and IC in terms of mesh currents. But this equation gives me the voltages VN minus VBN and VBN minus VCN in terms of impedance matrix and this current matrix. So therefore I can write this current matrix like this. What I will do, if I have to find this I1 I2 matrix, I will write it like this: I1 I2 is equal to, this impedance matrix is ZA plus ZB and then minus ZB and then here minus ZB again, and this is ZB plus ZC inverse, because when I find I1 by I1 I2, so it goes here and it becomes inverse multiplied by this voltage matrix, which is VAN minus VBN, first row, and second row is VBN minus VCN. Okay, so therefore my current matrix is given by this inverse of impedance matrix multiplied by this voltage matrix. So I can also write it as I1 I2 equal to 1 by delta or 1 by delta Z. Let me call this 1 by delta Z. Then what I will do, I will write first this ZB plus ZC, and then this minus ZB will become plus ZB, and here also it will become plus ZB, and then this term is ZA plus ZB. I mean, when you find inverse of this matrix, it will be 1 by delta Z into this matrix, into VAN minus VBN, and second row is VBN minus VCN. Okay. No, so this, let us call this equation as equation 1, where you have to define this delta Z. What is delta Z? Delta Z is this into this, that is ZA, ZB plus ZC into ZA plus ZB minus this into this, ZB into ZB is ZB square, or delta Z is equal to ZB into ZA is ZA ZB plus ZB into ZB is ZB square plus ZC into ZA is ZC ZA plus ZC into ZB is ZB ZC minus ZB square. Minus ZB square plus ZB square cancels. So this delta Z comes out to be ZA ZB plus, I will first write this term, ZB ZC plus ZC ZA. So this is your delta Z. So substitute this delta Z here. You know these load impedances, you know ZA, you know ZB, you know ZC. So you can get these currents. Let us from equation 1 try to find out these currents. So from equation 1, what is current, mesh current I1? It is 1 by delta Z times this thing, this into this plus this into this. So this is ZB plus ZC into VAN minus VBN plus ZB into this, ZB into VBN minus VCN. Okay, let us simplify it. So this will be 1 by delta Z, and delta Z just few moments back we have found. So ZB into VAN is VAN ZB plus ZB plus minus is minus VBN ZB. So it will be minus VBN ZB plus VAN ZC minus VBN ZC plus this is VBN ZB minus VCN ZB. Okay, this is it. So this is minus VBN ZB, this is plus VBN ZB, so they cancel out. So therefore what will you get? So therefore you will get mesh current I1 equal to 1 by delta Z times Let me take VAN out. So my first term is VAN times, this is VAN, this is VAN. So it is ZB plus ZC. Okay, ZB plus ZC. Then I have VBN term minus VBN ZC. VBN ZC. And then I have VCN term minus VCN ZB. Okay. So this is my equation for current I1. Let me call this equation as equation 2. Similarly, I can find mesh current I2. Where is the matrix? Let me write matrix again for you. Matrix is this. Sorry. This is the current matrix I1, I2 is equal to 1 by delta Z into ZB plus ZC, ZB, ZB, ZA plus ZB into VAN minus VBN and VBN minus VCN. I use this matrix to find out I1, mesh current. Similarly, I can from this matrix find I2. What is I2? I2 is 1 by delta Z into this, that is ZB into VAN minus VBN plus this into this, that is ZA plus ZB into VBN minus VCN, right? So that will be equal to 1 by delta Z times VAN ZB minus VBN ZB plus VBN ZA minus VCN ZA plus VBN ZB minus VCN ZB. Let us see what cancels. VBN ZB minus and VBN ZB plus, they cancel. So therefore, it will be equal to 1 by delta Z times VAN is only one term here. So it will be VAN into ZB, and where is VBN? VBN is here. So plus VBN ZA. Okay. So that is this term, this is gone, and we have two VCN terms here. So I will take VCN out common, minus VCN times ZA plus ZB. This is my mesh current I2. Let me call this equation as equation 3. So I have now two equations. One equation is for mesh current I1 and another equation is for mesh current I2. I1 is here. Let me write I2 also closer to this. So I2 is equal to 1 by delta Z times VA and ZB plus VB and ZA minus VCN times ZA plus ZB. This is equation 3. So these are two equations for mesh currents. And once you know the mesh currents, you can find the line currents, because if you redraw this circuit, three-phase circuit, this is ZA, this is IA, this is VBN, this is ZB, and this is IB. This is phase voltage VCN, this is load impedance ZC, and this is line current IC, and this is load neutral, this is supply neutral. Okay, and this is your mesh current I1 and this is your mesh current I2. What is now, you have found mesh currents I1 and I2 from the matrices, from the matrix. Once you know the mesh currents, you can find the line currents. Therefore, line current, therefore I will write line currents are as, let me first of all write line current IA. Now line current IA is same as mesh current I1. So it is same as mesh current I1. No change at all. So, and that is equal to 1 by that is equal to, I will write here, IA is equal to I1, and I1 is given above in equation 2. So 1 by delta Z times VAN into ZB plus ZC minus VBN into ZC minus VCN into ZB. So this is my line current IA. This is how we can compute IA. If you know delta Z, and you already know what is delta Z. Delta Z we have computed. Delta Z is ZA ZB plus ZB ZC plus ZC ZA. You know phase voltage VAN, you know phase voltage VBN, you know phase voltage VCN. It will be given in the problem. You know the load impedances ZA, ZB, ZC. Substitute here and you will get line current IA. So once you know line current IA, what will be line current IB? Now this line current IB in terms of mesh currents will be I1 minus I2. Okay, or I2 minus I1, क्योंकि I2 ये है, I2 is in this direction and I1 is in this direction. So it is I2 minus I1. So similarly, line current IB is equal to I2 minus I1. Okay, and what is your I2? I2 is 1 by delta Z. I will take 1 by delta Z common. This is VAN ZB plus VBN ZA. I will expand this. Minus VCN ZA minus VCN ZB. Okay. And it is minus I1. I1 is this. इसमें पहली टर्म है माइनस जब हम कर रहे हैं. So this is VAN ZB, so it will be minus VAN ZB. दूसरी टर्म है plus VAN ZC, since you are subtracting it is minus, so it will be minus VAN ZC. Minus VAN ZC. उसके बाद ये minus VBN ZC है, it will become plus VBN ZC. And similarly, this will become plus VCN ZB. Fine. Now VAN ZB plus VAN ZB minus, similarly VCN ZB plus VCN ZB minus, they will cancel out. So therefore you will get IB. So therefore what will be IB? Therefore line current IB will be 1 by delta Z times, let me find VAN term first. Okay, my first term is this, VA minus VAN ZA minus VAN ZC, and then I will write VBN term. And where is VBN term? This is VBN ZC and this is VBN ZA. Okay, I will take VBN common plus VBN. Inside I will get ZA plus ZC. ZA plus ZC. Okay, and then I am left with this term minus VCN ZA minus VCN ZA. So this is my line current IB. Okay, ZA plus ZC VBN minus ZA VCN and minus ZC VAN. This is my IB. Okay, so once you have IB, then you have to find third line current IC. So what is line current IC? देखिए आपकी I2 ऐसे है mesh current. IC is same as I2. ठीक है ना? But direction is different. IC you are assuming in this direction, but I2 is in this direction. So IC is equal to minus I2. Okay, and I2 is already given to you. It is here. So it is 1 by delta Z. जब हम माइनस लिखते हैं, ये माइनस अंदर जाएगा. It's minus I2. So it will be minus VAN ZB minus VBN ZA. Okay, then this minus plus हो जाएगा, plus VCN ZA plus VCN into ZB. Okay, so your IC will be now equal to 1 by delta Z times where is ZA? VAN. VAN, this I will write minus VAN ZB, right? Minus VAN ZB. Now VBN is this, minus VBN ZA, and then I will write VCN term. I have two VCN terms, plus VCN I will take common. inside I will get ZA plus ZB. So it is same as this, minus VAN, here it is plus VAN ZB, here it will be minus VA. Here it is positive term, here it will be negative term. Here it is negative term, here it will be positive term, because IC is not I2, IC is minus I2. I2 you have already computed from equation 3, so make it minus I2, so this is your IC. So this is how you solve a three-phase unbalanced circuit, where the load is star connected, source is also star connected, but load is unbalanced. This is how you solve, how you find the line currents IA, IB, IC in terms of mesh currents. Once you know the mesh currents, you find line currents, and then you find these line currents IA, IB, IC in terms of system parameters, that is phase voltages VAN, VBN, VCN, and load impedances ZA, ZB, ZC. Okay, so this makes our computations easy. So this is how you solve the circuit. Another way of solving the circuit and finding line currents is, for example, I will write here alternatively. Alternatively, you can find this line current IA also. IA is equal to VAN minus VNN by ZA. Since this is three-phase, three-wire system, neutral of load is not connected neutral of source. So there will be definitely some voltage between the two neutrals. Load neutral and source neutral, in between the two there will be some voltage. So therefore, if you find line current IA, it will not be VAN by ZA, it will be VAN minus this neutral to neutral voltage, VAN minus VNN by ZA. Similarly, IB, line current IB, will be phase voltage of phase B, VBN, minus neutral to neutral voltage, minus VNN by ZB. Similarly, you can find IC, which is VCN minus VNN by ZC. Okay, if you apply Kirchhoff's current law at neutral, apply KCL at load neutral N. So you will get IA plus IB plus IC equal to 0, because you are not providing any neutral wire. There is no path for the neutral current to flow. So the sum of three currents, IA plus IB plus IC, is equal to 0 by KCL. So what is IA? IA is VAN minus VNN by ZA plus, what is IB? IB is this equation, VBN minus VNN by ZB plus IC. IC is given by this equation, VCN minus VNN by ZC is equal to 0. So we can further solve it. So I can write VAN by ZA plus VBN by ZB plus VCN by ZC, okay, is equal to this is VNN by ZA. VNN by ZA, I take it to right hand side. On the left hand side it is minus, on right hand side it will become plus. Similarly, plus VNN by ZB. Similarly, plus VNN by ZC. Or you can write VAN by ZA plus VBN by ZB plus VCN by ZC is equal to, if you take VNN out, what will you get? 1 by ZA plus 1 by ZB plus 1 by ZC. तो यहाँ से आपको न्यूट्रल टू न्यूट्रल वोल्टेज मिलेगी. VNN will be equal to this divided by whole divided by this 1 by ZA plus 1 by ZB plus 1 by ZC. So that is VNN is equal to this, 1 by this into this, that is VAN by ZA plus VBN by ZB plus VCN by ZC. This is how you find neutral to neutral voltage. Or you can also write this neutral to neutral voltage, you can write like this. if you take LCM, LCM is ZA, ZB, ZC, and you take that up, that will be ZA, ZB, ZC divided by, here it will be ZA, ZB plus ZB, ZC plus ZC, ZA. Okay, multiplied by this VAN by ZA plus VBN by ZB plus VCN by ZC. This is how you can find neutral to neutral voltage. You know the load impedances ZA, ZB, ZC. You know source phase voltages VAN, VBN. Substitute either in this equation or in this equation. That will give you neutral to neutral voltage. And once you know the neutral to neutral voltages, then you can find the line currents. Like, for example, what is line current IA? That is VAN minus VNN by ZA. Line current IB is equal to VBN minus VNN by ZB. And line current IC is equal to VCN minus VNN by ZC. VAN, VBN, VCN are phase voltages. It will be given to you. Load impedances ZA, ZB, ZC are given to you. The only unknown to you was neutral to neutral voltage, and you can use this equation or this equation for finding neutral to neutral voltage in terms of source voltage and in terms of load impedances. Once you know neutral to neutral voltage, substitute in these equations. That will give you line currents. Line currents in terms of neutral voltage. So I have given you two methods of finding these line currents. One, if you apply the mesh current analysis and find the line currents IA, IB, IC. I have already given you some equations for that. We have derived those equations in terms of using the mesh current analysis. Another way is to find line currents IA, IB, and IC in terms of neutral to neutral voltages and source voltages like this. And neutral to neutral voltage can be found from this equation. Okay, let us make some I will again write this neutral to neutral voltage. Okay, we will have some inferences from these equations. First thing is, let us suppose source, three-phase source is balanced and three-phase load is also balanced. So I will write here, if both source voltage and load impedances are balanced. If both source voltages and load impedances are balanced, our equations will get modified. So that means ZA is equal to ZB is equal to ZC is equal to Z. Okay. Therefore, what will be neutral to neutral voltage? We already know neutral to neutral voltages ZA, ZB, ZC divided by ZA, ZB plus ZB, ZC plus ZC, ZA into VAN by ZA plus VBN by ZB plus VCN by ZC. Just 1 minute back, we have derived this equation. So if source voltages are balanced, that is VAN, VBN, VCN, they are having same magnitude and phase shift of plus minus 120 degrees, so balanced set of three-phase voltages. And if load impedances are also balanced, that is ZA is equal to ZB is equal to ZC equal to Z, then what will be neutral to neutral voltage? So ZA, ZB, ZC, both, all the three are Z, so it will be Z. Z into Z into Z is Z cube divided by, this will be Z square plus Z square plus Z square into, see, this is ZA, ZB, ZC. This is Z, this is Z, this is Z. So this can be taken outside, that will be Z itself. Okay, so what will you get inside is VAN plus VBN plus VCN. So that is equal to Z cube divided by Z square plus Z square plus Z square is equal to 3Z square into Z is 3Z cube into VAN plus VBN plus VCN. Z cube and Z cube goes. So you will get neutral to neutral voltage equal to 1 by 3 times VAN plus VBN plus VCN. Interestingly, for a three-phase balanced system, if source voltages are balanced, what is then phasor sum of three phase voltages? VAN plus VBN plus VCN. What is that equal to? That is simply equal to 0. So therefore, neutral to neutral voltage will be simply equal to 0. So there will not be any voltage between the two neutrals if source is balanced and if load impedances are also balanced. So neutral to neutral voltage is 0, and you can very easily find then line current will be VAN minus VNN by ZA. Since VNN is 0, so it is simply VAN by ZA. Similarly, IB, you can find IB, and similarly you can find IC. So this is first inference. Second inference is if both source voltages are, let me first of all assume if supply voltage, that is source voltages, are balanced but load impedances are unbalanced. Load impedances are unbalanced. Source voltages are balanced but load impedances are unbalanced. In that case, what will be neutral to neutral voltage? Neutral to neutral voltage is given by ZA, ZB, ZC divided by ZA, ZB plus ZB, ZC plus ZC, ZA into VAN by ZA plus VBN by ZB plus VCN by ZC. Although source voltages are balanced, VAN, VBN, VCN are balanced, but impedances are not balanced. That is, ZA is not equal to ZB, not equal to ZC. So this will give you different amounts of currents. So you cannot make this sum equal to 0. Similarly, here you have different impedances. ZA, ZB, ZC are different. So therefore, you have to use this entire equation for calculation of neutral to neutral voltage. So therefore, neutral to neutral voltage will not be equal to 0. In that case, you have to find neutral to neutral voltage. And once you know neutral to neutral voltage, then you can find line current. For example, it is equal to VAN minus VNN by ZA. You know VAN, and from this equation you will find VNN divided that by ZA, you will find IA. Similarly, you can find IB. Similarly, you can find IC. Okay, so this is second inference. Third inference is if supply voltages are unbalanced. If supply voltages are unbalanced but load impedances are balanced. We are taking different combinations, but load impedances are balanced. In that case, our neutral to neutral voltage is given by ZA, ZB, ZC whole divided by ZA, ZB plus ZB, ZC plus ZC, ZA into VAN by ZA plus VBN by ZB plus VCN by ZC. That is equal to load impedances are balanced. So this is ZA, ZB, ZC. ZA is equal to ZB is equal to ZC is equal to Z are balanced. So this will be Z cube by 3Z cube. It will be Z squared, Z squared, Z squared into Z, Z cube. So that will be Z cube plus Z cube plus Z cube, 3Z cube. Into, inside you will get VAN plus VBN plus VCN. So Z cube and Z cube goes. So VNN in that case will be 1 by 3 times VAN plus VBN plus VCN. You cannot make VAN plus VBN plus VCN equal to 0 because supply voltages are unbalanced. So this is equal to V0, where V0 is zero sequence voltage. In terms of sequence components, the sum of the three phase voltages will not be 0 because the supply voltages are unbalanced. So sum of three voltages, phasor sum of three voltages is equal to zero sequence voltage. It will have some positive value, some magnitude. So therefore, you can find neutral to neutral voltage. So in this case also, neutral to neutral voltage will not be equal to 0. It will be equal to 1 by 3 times 0 sequence voltage V0, which is equal to VAN plus VBN plus VCN. And fourth possibility is that both are unbalanced. If both supply voltages and load impedances are unbalanced, in that case you have to use this entire equation, VNN equal to ZA, ZB, ZC divided by ZA, ZB plus ZB, ZC plus ZC, ZA times VAN by ZA plus VBN by ZB plus VCN by ZC. Your impedances are unbalanced, your source voltages are also unbalanced. So in this case, this entire equation has to be used and you have to find VNN. And in this case also VNN will not be equal to 0. Fifth inference is that for a three-phase, three-wire system, the system that I have shown previously, the diagram, that is three-phase, three-wire system. Neutral wire is not given there. We have already found that if source voltages and load impedances are unbalanced, or if any one of the two is unbalanced, so neutral to neutral voltage is not equal to 0. But the sum of three line currents, IA plus IB plus IC, is equal to 0 because this is your three-phase system. You are not providing any neutral. There is no neutral. This is N, this is N, this is ZA, this is ZB, this is ZC, this is VAN, this is VBN, this is VCN, this is line current IA, this is line current IB, this is line current IC. Just from above analysis, we have found that this neutral to neutral voltage will not be 0 if either source is unbalanced or load is unbalanced or both are unbalanced. Then in that case, VNN is not equal to 0. But the sum of the three currents, phasor sum of three line currents, IA plus IB plus IC, is 0 because we are not providing any path for this neutral current to flow. So sum of the three currents is 0. And finally, the last inference is for a three-phase, four-wire system. If you are providing fourth wire also, like in our distribution systems, we have fourth wire also. This load neutral is connected to supply neutral. So this is your, neutral current, IN. Okay. So this is the neutral current and you are providing fourth wire also. 1, 2, 3, 3 and fourth wire is neutral wire. In this case, VNN will always be equal to 0 when load neutral is connected to source neutral. Whether your system is balanced or unbalanced, this neutral to neutral voltage will always be equal to 0. But the sum of three currents, phasor sum of three line currents, IA plus IB plus IC, will not be equal to 0. It will be equal to neutral current. Okay, that is this. Because you are providing path for this current to flow. It will be equal to neutral current. So therefore, what is the conclusion? The summary is, number one, if source is balanced, load is also unbalanced, then neutral to neutral voltage, we have already found it is equal to 0. Whether it is a three-phase, three-wire system or a three-phase, four-wire system, neutral to neutral voltage is 0. After that, if you consider three-phase, three-wire system, if source voltages are balanced but load impedance is unbalanced, then also neutral to neutral voltage is not 0. Third possibility is that load impedances are balanced but source voltages are unbalanced. In that case also, neutral to neutral voltage is not equal to 0. We have found that. And finally, if both are unbalanced, source is unbalanced, load is also unbalanced, in that case also neutral to neutral voltage is not equal to 0. And fifth is that for this three-phase, three-wire system, neutral to neutral voltage in most of the cases is not equal to 0. Except when both source as well as load are balanced. But if any one of them is unbalanced or both of them are unbalanced, neutral to neutral voltage is never equal to 0. And the sum of three line currents, phasor sum of three line currents, is 0. And if you are providing fourth wire, there is three-phase four-wire system. The neutral to neutral voltage is always zero, whether your system is balanced or unbalanced. Neutral to neutral voltage is zero, but the sum of three phasor sum of three currents, IA plus IP plus IC, is not equal to zero. It is equal to neutral current. Okay. That was about three-phase star connected load. Now let us consider three-phase delta connected unbalanced system. Three-phase delta connected unbalanced load. Let us suppose our load is unbalanced, but it is not star connected. It is delta connected like this. How to solve a delta connected system? This is the load. This is A, node A, node B, and node C. This is line current IA. This is line current IB, and this is line current IC. This is load admittance YL AB between A and B. This is load admittance YL CA between C and A, and this is load admittance YL BC. And these are the, there are phase currents also. So these are load admittances and these are line currents. What is this load admittance YLAB? It is GLAB conductance plus susceptance JBLAB. Similarly, YLBC, that is this admittance, is equal to GLBC plus JBLBC, and this admittance YLCA is equal to GLCA plus JBLCA. Anyway, these are the admittances. In order to solve this circuit, find these currents, line currents, our aim is to find the line currents for this delta connected unbalanced load, IA, IB, IC. It will be very difficult to solve this circuit in its form. What we do, we transform or convert this delta connected load into its equivalent star connected load, and our equivalent star connected load becomes like this. How? I will show you the equations with the help of which you can transform a delta connected system into a star connected system. I hope you have already learned those techniques in your BTech electrical engineering. This is the load neutral N. Okay, this is A, this is B, this is C. Okay, this is impedance, load impedance ZLA, this is ZLB, and this is ZLC. And this is my line current IA, this is my line current IB, and this is my line current IC. If this delta connected load is equivalent to this, if this star connected or Y connected load has to be equivalent to this delta connected load, then terminal characteristics should not change. Terminal characteristics means this IA, IB, IC, these line currents drawn by this equivalent star connected load should be exactly equal in magnitude, or should be exactly same as the line currents IA, IB, IC drawn by this delta connected load. If these line currents are not equal to these line currents, then we can say this is not equivalent to this. So in order to have equivalence, you have some equations. For example, you have to find this ZLA, this impedance of phase A or line A, ZLA. In terms of this, it is given by ZL, it is given by ZLAB. See, this A is between AB and CA into ZLCA divided by sum of the three line impedances, ZLAB plus ZLBC plus ZLCA. Okay, आपने स्टार डेल्टा ट्रांसफॉर्मेशन पढ़ा है? in your basic electrical engineering circuit theory. Same approach you can use here. This is delta, you have transformed it into its equivalent star or equivalent y. This impedance ZLA is equal to, देखिए A यहाँ है, A पे ये दो impedances है, so multiply these two impedances divided by sum of the three impedances. Similarly, you have to find this ZLB. B is here, ये point, इस point पे ये दो impedances है, although ये admittances है, but you can consider them impedances. So this is ZLAB into ZLBC divided by sum of three impedances, ZLAB plus ZLBC plus ZLCA. And similarly, ZLC ये is equal to C ये point है. Okay, so it is ZLBC into ZLCA. ZLBC into ZLCA divided by sum of three impedances, ZLAB plus ZLBC plus ZLCA. That's it. It makes our job very easy. So once you know these impedances, generally these impedances are given to you, even if admittances are given to you, YLAB is given to you. You can find impedance ZLAB is reciprocal of this admittance. So you can, similarly, what is ZLBC? ZLBC is 1 by YLBC and ZLCA is 1 by YLCA. So substitute in these. So you will get equivalent impedances and you can transform this delta connected load into equivalent Y connected or star connected load. And once you know this, it is very easy to solve this star connected load. Then same equation जो अभी थोड़ी देर पहले हमने method use किया. I mean, if you have to now find this IA will be equal to VAN minus VNN by ZLA. Similarly, IB will be equal to VBN minus VNN by ZBL. And IC, line current IC, will be equal to VCN minus VNN by ZCL. ये ZCL है. And what are these ZLA, ZLB and ZAL, ZBL and ZCL? They are equivalent impedances of this delta connected load. And you can then solve it. If you know VNN and you already know what is mathematical expression for VNN. If VNN is not equal to 0, your system is unbalanced. You can calculate VNN using the same equation. You know what is VNN. VNN is ZLA into ZLB into ZLC divided by ZLA, ZLB plus ZLB, ZLC plus ZLC, ZLA into, then you know, VAN by ZLA plus VBN by ZLB plus VCN by ZLC. Same these equations which we have just few moments back derived for a Y connected load, they can be used for this delta connected load also, and in this way you can find this. Okay, so this is how you transform a delta connected load into its equivalent Y connected load and solve it. Let us try to solve a numerical example. We'll take a numerical problem and solve that. This is our example number 1. This is my question. Consider a three-phase system supplying a delta connected unbalanced load with ZLA equal to RA equal to 10 ohms, ZLB equal to RB equal to 15 ohms, and ZLC equal to RC equal to 30 ohms as shown. Determine the voltage between neutrals and find the phase currents. Assume a balanced supply voltage with an RMS value of 230 volts. Find out the vector and arithmetic power factor. Comment upon the result. This is given to us. This is given to us. We have a delta connected system like this. This is A, this is B, this is C. This is line current IA, this is line current IB, this is line current IC. Okay. The circuit is purely resistive in nature. इसका equivalent star आप बनाइए, इसका equivalent star ये बनेगा. This is A, this is B, and this is C. ये आपकी line current है IA, this is line current IB, this line current or phase current IC. You have to find these three line currents. Line current IA, line current IB, line current IC. And it is given that ZLA, या आपका ZLA है. It is purely resistive in nature, RA equal to 10 ohms. Yeah, actually, how do we, this is our delta connected system. We transform this delta connected system into its equivalent Y connected system, or we are not supposed to perform those calculations here. Those are already given in the problem. ZLA equal to RA equal to 10 ohms. It is itself given in the problem. But if you are not given this, you are given these parameters, then you can use just few moments that I have shown you how to transform a delta connected load into its equivalent Y connected load using those equations. So that those will give you ZLA, ZLB, and ZLC. What is ZLB? It is also given ZLB is equal to RB, which is 15 ohms. It is given in the problem here. And ZLC is RC. ZLC is equal to RC. It is given as 30 ohms. So load is unbalanced because this phase is having an impedance. This phase of load is having an impedance resistance of 10 ohms. B has a resistance or impedance of 15 ohms. And C has an impedance or resistance of 30 ohms. So what you have to find? You have to determine the voltage between the neutrals. Okay, between the neutrals means यहाँ से आपका supply system भी है. You have a supply system on this side, ऐसे, which is also star connected. So they are connected like this. This is VAN, this is VBN, and this is VCN. Or rather, this is VBN, and this is VCN. Okay, this is the supply neutral. You have to find voltage between these two neutrals. इसको हम ऐसे भी ड्रॉ कर सकते हैं ना. Simply we can draw like this. This is VAN. This is ZLA equal to RA equal to how much? 10 ohms. This is VBN. This is ZLB equal to RB. RB is how much? It's given here, 15 ohms. This is VCN. And this is ZLC equal to RC. RC is how much? 30 ohms. This is load neutral and this is supply neutral. In the problem, everything is given to you. This is equivalent Y or equivalent star of this delta load, and these individual phase resistances, load resistances, equivalent resistances are given in the problem itself. And you have to find neutral to neutral voltage. You can draw it like this, or you can equivalently draw it like this. This and this represents the same thing. So you have to find this neutral to neutral voltage. And we know how to find neutral to neutral voltage. Let us try to solve it. Neutral to neutral voltage is ZA, ZB, ZC divided by ZA, ZB plus ZB, ZC plus ZC, ZA into VAN by ZA plus VBN by ZB plus VCN by ZC. In fact, it is ZLA, ZLB and ZLC, or you can simply call them ZA, ZB, ZC. Or we can write neutral to neutral voltage is equal to, see, these impedances are pure resistances, RA, RB, RC. So I can simply write RA, RB, RC divided by RA, RB plus RB, RC plus RC, RA into VAN by ZLA. ZLA is RA plus VBN by ZB or ZLB, which is RB, plus VCN by ZLC, that is VCN by RC. Substitute the values. RA is how much? 10 into RB is 15 into RC is 30. Divided by RA, RB, that is 10 into 15 plus RB, RC, 15 into 30 plus RC, RA, that is 30 into 10 whole multiplied by VAN. Okay, it is given in the system that source voltage is source is balanced. So VAN is V at an angle of 0 degree by RA. RA कितना है? 10 ohms. Plus VBN is V at an angle of minus 120 degrees divided by RB. RB कितना है? 15 ohms. Plus VCN is V at an angle of plus 120 degrees by RC 30 ohms. ये अगर आप निकालेंगे, this will come out to be 4500 by 900. ओके, यहाँ आप LCM 30 निकालिए, ये बनेगा 3V at an angle of 0 degrees plus 2V at an angle of minus 120 degrees plus V at an angle of plus 120 degrees. Okay, further simplification will give, this is 4500. So this will give, ये V भी मैं बाहर निकालता हूँ और ये नीचे 30 भी बाहर निकालता हूँ. This will give 4500 by 900 into V by 30. V इन तीनों में कॉमन है और 30 नीचे है, so V by 30. Okay. Now I will get 3 at an angle of 0 degree, that is 3 itself, plus 2 at an angle of minus 120 degrees. What is minus 120 degrees? Phase angle of minus 120 degrees means cos minus 120 degrees plus J sine minus 120. What is cos minus 120 degrees? Cos minus 120 degrees or cos plus 120 degrees is minus 1 by 2. Plus J sine minus 120 degrees is, sine 120 degrees is root 3 by 2, but it is minus, so it is minus J root 3 by 2. ठीक है, हो गया ये. प्लस तीसरे में है 1 into cos 120 degrees, it is again minus 1 by 2 plus J sine 120 degrees plus J root 3 by 2. Okay, so when you solve it, it comes out to be V by 2 root 3. It comes out to be, I'm skipping some steps, you can solve it very easily. V into 0.25 minus J 0.1443. This is what we get. So therefore, neutral to neutral voltage V and N will be equal to V by 2 root 3 at an angle of minus 30 degrees. See, cos minus 30 1 by 2 root 3 into cos minus 30 degrees plus J sine 30 degrees, वो आपको ये देगा. और simply it will be equal to 66.39 at an angle of minus 30 degrees. This is in rectangular coordinates. When you transform it into polar coordinates में ये बनेगा. Under root of 0.25 square plus 0.1443 square will be this at an angle of minus 30 degrees into V. V तो है ही, V is already there. Okay, so this is neutral to neutral voltage. And once you have the neutral to neutral voltage, you can now find currents. Therefore, what is line current IA? Line current IA is VAN minus VNN by RA. What is VAN? VAN is V at an angle of 0 degrees minus VNN आपका ये है 66.39 at an angle of minus 30 degrees by RA. RA कितना है? 10 ohms. If you solve it, you'll get IA equal to 17.56 at an angle of 10.89 degree amps. This is your line current IA. Okay, so in fact it will be ये अगर आप solve करेंगे ना, it will be V into 0.075 plus J 0.0144. V is given in the problem 230 volts. तो यहाँ 230 से मल्टीप्लाई करो. So 230 into whole this, it will come out in rectangular coordinates. Transform that into polar coordinates, you will get IA. In a similar way, you can get line current or phase current IB. So what is phase current IB? That is VBN minus VNN by RB. VBN is V at an angle of minus 120 degrees minus VNN is 66.39 at an angle of minus 30 degrees into V by RB कितना है 15 ohms. You solve it, I'll give you final result. It will come out to be 15.94 at an angle of minus 136.1 degree amps. This is IB. In a similar way, you can find IC. IC is equal to VCN minus VNN by RC. VCN is V at an angle of plus 120 degrees minus VNN is 66.39 at an angle of minus 30 degrees V by 30. So that will give you current, line current IC, that is 9.64 at an angle of 126.58 degree. So you can see the three currents are unbalanced. What was IA? IA भी थोड़ी देर पहले हमने निकाला. IA was 17.56 at an angle of 10.89 degree amps. IB has a different magnitude, 15.94 amperes, and IC is 9.64 amperes. So three different line currents are there because your load is unbalanced. So this is part B of the problem. In part C, you have to find vector apparent power. It is given to us that find out vector and arithmetic apparent power and comment upon the results. So what is vector apparent power? It is P plus JQ. तो सबसे पहले हम SA निकालेंगे, apparent power associated with phase A, that is VA into IA star. Okay, VA is 230 volts into what is line current. अभी थोड़ी देर पहले हमने line current IA निकाली, that is 17.56 at an angle of minus 10.81 degrees. There it was at an angle of plus 10.81 degrees, but since it is complex conjugate, so it will be minus 10 point this. So this will be 3976.12 minus J757.48 VA, volt ampere. Similarly, you can find SB. SB is VB into IB complex conjugate. VB is 230 at an angle of minus 120 degrees. Okay, and IB अभी थोड़ी देर पहले हमने निकाला. How much was IB? IB was 15.94 at an angle of minus 136.1. So it will be plus 136.1 degrees because we have complex conjugate. So that will be equal to 230 into this. 230 into 15.94 at an angle of minus 120 degrees plus 136.1 degrees. This minus this. So that will give us SB, and I have calculated SB, and as per my calculation, SB is 3522.4 plus J1016.69 volt ampere. Please verify these figures. ये figures of verify कर लीजिए. Similarly, you can find SC. SC is VC into IC complex conjugate. VC is 230 at an angle of plus 120 degrees. And IC अभी थोड़ी देर पहले हमने निकाली 9.64 at an angle of 120. It is 126.58 degrees. लेकिन जब complex conjugate करेंगे इसका, so it will be minus. So multiply these and that will give us SC, apparent power associated with phase C, as 2202.59 real part minus J254.06, ये volt ampere है. So therefore, you have SA, you have SB, you have SC. So therefore, what is P? P is equal to PA plus PB plus PC. इन तीनों ये जो आपके SA है, it is PA plus JQA, जो अभी थोड़ी देर पहले हमने निकाला. SB is PB plus JQB and SC is equal to PC plus JQC. आप ये तीन रियल पार्ट्स ऐड करें which we have just now calculated. So that will give you total three-phase power, real power of course, and this comes out to be 9692.11 watts. और अगर आप total reactive power निकालेंगे, that is QA plus QB plus QC, that will be equal to 0. That has to be 0 because we have a purely resistive circuit. All the three phases, although unbalanced, but they have resistances, no reactances are there. So therefore, what is vector apparent power? It is P plus JQ. Okay, P is 9692.11 plus J0. So this is your vector apparent power. Therefore, vector apparent power is 9692.11 volt ampere. Once you know vector apparent power, now we can find arithmetic apparent power. What is arithmetic apparent power? If you remember, arithmetic apparent power is SA plus SB plus SC. It's the sum of three apparent powers. अभी थोड़ी देर पहले आपने तीनों apparent power निकाले, add them up in this fashion, that will give you arithmetic apparent power. I have calculated that, and as per my calculations, that is 9922.2 volt ampere. So I have vector apparent power. I have the figure for arithmetic apparent power. So therefore, what will be vector power factor? Vector power factor will be P by SV. P is total active power, which is 9622.11, और SV भी यही है, SV यही है 9622.11. So that means the vector apparent power is unity. It has to be unity because load is purely resistive in nature, but it does not take unbalance into consideration. What will be arithmetic power factor? Arithmetic power factor will be P by SA. P is 9622.11 by SA. The arithmetic apparent power is 9922.2. So that will give us arithmetic apparent power, and arithmetic apparent power is less than unity. It is 0.9769. So therefore, arithmetic power factor is less than unity, is less than vector apparent power, and of course it is less than unity. It is less than unity because vector apparent power is unity. It is less than unity. Why is it so? Because we have to go back to the earlier lectures when we were discussing three-phase unbalanced systems. In a three-phase unbalanced system, the line losses are very large as compared to the line or feeder losses of a balanced three-phase system. And to take those line losses into consideration, we define another type of apparent power. In addition to vector apparent power, we define arithmetic apparent power, and this arithmetic apparent power is greater than vector apparent power because it takes into consideration the additional losses in the feeder or in the line due to unbalance in the system. Okay, so therefore the this arithmetic power factor will be less than vector power factor. For example, in this example, the vector power factor was 1, but arithmetic power factor is less than 1. It is 0.9769 because it takes into consideration the additional feeder losses or additional line losses which are there because of the unbalance in the load currents. Okay, so that is about the comments. So that is the solution of this problem. So in the end, we will discuss an alternate approach to solve a delta connected unbalanced system or delta connected unbalanced load. Just few moments back we have seen how we can solve a delta connected system. What we have to do, we have to transform the delta connected system into its equivalent Y or star connected system, and then you have to find neutral to neutral voltage. Once you know the neutral to neutral voltage, then you find three line currents like IA is equal to VAN minus VNN by ZA, IB is equal to VBN minus VNN by ZB, and IC is equal to VCN minus VNN by ZC, where VNN is neutral to neutral voltage. Is it possible for us to find these line currents without finding the neutral to neutral voltage? Because you have to find this neutral to neutral voltage to find line currents. Can we skip? Can we find the line currents IA, IB, IC without finding the neutral to neutral voltage? Answer is yes. For that purpose, we can use an alternate approach. What is that alternate approach? Let me explain that with the help of this system. This is our three-phase unbalanced delta load, A, B, and C. This is line current, the phase current IAB. This is phase current, similarly IBC, and this is phase current ICA. And these are three line currents. This is line current IA, this is line current IB, and this is line current IC. This is the admittance YLAB between A and B. The admittance in the phase, in this phase between A and C, is YLCA, and this admittance is YLBC. Now, what is VA? Let us suppose source voltage is balanced. VA is equal to V at an angle of 0 degree. Okay. What is VB? VB is equal to V at an angle of minus 120 degrees, and that is equal to alpha square V. Because you already know alpha square when we were discussing the sequence components. Alpha square, or या हमने उसको A कहा था. We had represented that by A, not alpha. A square V. We defined this A square as A square is equal to e raised power minus minus j, e raised power minus j, e raised power j 4 pi by 3, and that was equal to minus 1 by 2 minus j root 3 by 2. Okay, and that was equal to cos minus 120 degrees plus j sine minus 120. If you find this, it is cos minus 120 degrees plus j sine minus 120. That will come out to be this. Okay. Similarly, VC is given V at an angle of plus 120 degrees, and that is given by A into V. Where what is this A? A is e raised power minus j 2 pi by 3. Okay, sorry, it is j 2 pi by 3, and it is equal to 1 at an angle of 120 degrees, and it is equal to minus 1 by 2 plus j root 3 by 2. We already know from when we were discussing the symmetrical components, वहाँ हमने ये use किया a square, these operators, and I also told you that 1 plus a square is equal to 0. Okay, so this is how you can represent VA, VB, and VC. VA is V at an angle of 0 degree, VB is A square VC, A square V, and VC is AV, A into V. VC is equal to A into V. Okay. So if you use this, then we can find line-to-line voltages. Therefore, what will be this line-to-line voltage? VAB. It will be VAN minus VBN. It will be, of course, VA minus VB. Or VA already हमारे पास है, that is V at an angle of 0 degree. Or simply we can write it V minus, what is VB? VB है A square V. And अगर आप V common निकालेंगे, so it will be V times 1 minus A square. ठीक है? This is how we can find this line-to-line voltage in terms of A, operator A. Similarly, what about VBC? Line-to-line voltage VBC. VBC will be equal to VB minus VC. और VB आपका क्या है? ऊपर भी आपने लिखा है, it's A square V minus VC है AV. So that will be V times A square minus A. Similarly, you can write VCA line voltage, which is VC minus VA. VC is AV minus VA is V. You take V out, so it will be A minus 1. V times A minus 1. Once you know these line voltages, VAB, VBC, VCA, you can find now these internal currents. For example, you can find this IAB. Therefore, what is this IAB? L. It is equal to VABL into ZABL. That is equal to VAB into YLAB. Okay, and you already know, just few moments back you have found this VAB. अभी थोड़ी देर पहले आपने VAB निकाला, line voltage VABL. VAB, what was that equal to? अभी थोड़ी देर पहले हमने निकाला, that was V times 1 minus alpha square. Yeah. So you can substitute it here. So it will be YLAB into V into 1 minus A square, not alpha A, 1 minus A square. Okay. So this is ILAB. Once you have found ILAB, you can find ILBC. What will be IBCL? That will be VBC into YBCL. That will be YBCL into VBC. VBC अभी थोड़ी देर पहले आपने निकाला in terms of operator A and A square. VBC is V times A square minus A. तो इसको substitute कर लीजिए. Similarly, ICAL will be equal to VCA into YCAL. That is equal to YCA into VCA. VCA किसके बराबर अभी हमने निकाला? V into A minus 1. So substitute कर लीजिए. Now our aim is not to find these internal phase currents IA, IAB, IBC, IC. We have to find these line currents IA, IB and IC. So therefore we can find line currents. Therefore line currents are, for example, what is line current IA? This line current IA is IAB minus ICA. It is IAB L minus ICAL minus ICAL. Okay. So that is your IA, IABL minus ICAL. So IABL अभी थोड़ी देर पहले आपने निकाला. What is IABL? That is YLAB into 1 minus alpha square V minus ICAL ये है. It is YCA into V into A minus 1. Okay. So this is your IA. So you can find IA. Similarly, you can find IB. IB ये है. It is this current minus this current. So it is IB is equal to IBCL minus IABL. It is this IBC minus IAB. So IB is equal to IBC is with you, IAB is with you. So IB will be equal to YLBC into A square minus A minus YLAB into 1 minus A square. Okay, whole multiplied by V. Multiplied by V. And similarly, you can find IC. What is IC? IC is equal to ICAL minus IBCL. And IC will be equal to, this is YLCA into A minus 1 minus YLBC into A square minus A whole multiplied by V. So this is, इसको भी whole multiplied by V आप ये बाहर निकाल सकते हैं. IA में भी V बाहर निकाल सकते हैं. So therefore this is IA in terms of line admittances and in terms of operators A square and A. So therefore यहाँ आपने तीनों line currents निकाली. ये आपको डेल्टा को equivalent Y में transform करने की जरूरत ही नहीं पड़ी. In the previous method, what we were doing, we had a delta connected unbalanced load. First step was to transform that into its equivalent unbalanced star connected load. उसके बाद find the neutral to neutral voltage. उसके बाद find the line currents IA, IB, IC. इस केस में आपने क्या किया? You had a delta connected load, of course unbalanced load. you did not transform it into equivalent y connected load. आपने ऐसे ही रखा delta, but and since you did not transform it into equivalent y connected load, you are not supposed to find neutral to neutral voltage. Okay, तो उसके बाद आपने क्या किया, you defined the operators, these line voltages, phase voltages in terms of operators a and a square. और उसके बाद आपने internal phase currents IABL, IBCL and ICL निकाली, और line currents are the vector phasor sum of these currents, and this is how you got IA, this IB given by this equation and IC given by this equation in terms of A and A square, and of course admittances and supply voltage. So you did not find neutral to neutral voltage. Yeah. You did not transform delta connected unbalanced load into equivalent star connected unbalanced load, and number two, you did not find neutral to neutral voltage. You find the line currents in terms of these operators A and A squares. Okay, so you can use this for solving a problem. Let us try to solve a numerical problem. It is given here. For example one, जो भी हमने एक example solve की थोड़ी देर पहले, compute the line currents by above expressions. You have to find, this is example 2, you have to find the line currents. The RA is given to us as 10 ohms, which is same as ZA, ZLA. ZLB is RB, it's given 15 ohms, and ZLC is equal to RC, it is given as 30 ohms. It is given in the problem, ये same problem है. Okay, VAL is equal to VA is equal to 230 at an angle of 0 degree volts. VB जो आपकी है, that is 230 at an angle of minus 120 degree volt. It is given in the problem itself. The source voltages are balanced, and VC is 230 at an angle of plus 120 degree volts. Okay. अब आपके पास आपको line current IA निकालनी है. And what is the mathematical expression for IA? It is YL AB, अभी थोड़ी देर पहले हमने लिखा, times 1 minus A square minus YL CA into A minus 1 into V. A square A आपको पता है, you don't know these admittances. For example, आपको YLAB निकालना है, उसके लिए आपको ये YLAB is 1 by ZLAB. उसके लिए आप ये फॉर्मूला यूज कर लीजिए, ZLC divided by ZLA into ZLB plus ZLB into ZLC plus ZLC into ZLA. Okay, ZLC is this 30 ohms divided by ZLA is 10 ohms. 10 into ZLB कितना है, 15 plus 15 into 30 plus 30 into 10. ये solve कर लीजिए. This will give you YLAB. Okay, and this YLAB comes out to be 1 by 90 Siemens. Similarly, you can find YLBC. YLBC is equal to देखिए YLAB में AB के बाद C आता है, तो BC के बाद क्या आता है, A, so it will be ZLA divided by same, denominator same रहेगा. ये trick है, this is how you can remember it. ZLA ZLB plus ZLB ZLC plus ZLC ZLA. आप ये value substitute कर लीजिए, and I have calculated it. You can verify. YLBC as per my calculations comes out to be YLAB कितना निकला था, YLAB थोड़ी देर पहले हमने निकाला है, that is 1 by 30 Siemens, not 1 by 90. वो correct कर लीजिए. YLBC is 1 by 90 Siemens. इसी तरह आप YLCA निकाल सकते हैं. YLCA, C भी है, A भी है, what is missing? B. So that will be ZLB divided by ZLA ZLB plus ZLB ZLC plus ZLC ZLA और ये मैंने कैलकुलेट किया है एज पर माई कैलकुलेशन, इट इज़ 1/60 साइमन। ओके, तो ये आपको मिल गए। सो देयरफॉर यू कैन नाउ फाइंड द करेंट्स। सो देयरफॉर व्हाट विल बी लाइन करंट IA? इट विल बी YLAB into 1 minus A square minus YLCA into A minus 1 whole multiplied by V. अब आप सब्स्टिट्यूट कर लीजिए। YLAB अभी थोड़ी देर पहले आपने निकाला, इट इज़ 1/30 साइमन्स इंटू 1 minus A square। A square है -1/2 minus J√3/2। ओके, माइनस YLCA भी आपने थोड़ी देर पहले निकाला, दैट इज़ 1/60। 1/60 ये आपने YLCA निकाला, इट इज़ 1/60 साइमन्स इंटू A minus 1। A क्या है आपका? A है -1/2 प्लस J√3/2 -1 इंटू V। सो ये जब आप सॉल्व करेंगे ये आएगा V इंटू 0.075 प्लस J 0.0144, ये आएगा 0.07637 एट एन एंगल ऑफ 10.89 डिग्रीज इंटू V। तो मल्टीप्लाई कर लीजिए V से। V आपकी 230 वोल्ट्स गिवन है इन द प्रॉब्लम। सो देयरफॉर IA will be equal to 0.07637 into 230 at an angle of 10.89 degrees. So that will give you IA, and IA comes out to be 17.56 at an angle of 10.89 degree amps. This is same जो अभी थोड़ी देर पहले हमने दूसरे मेथड से निकाला। Just check it. There also this IA was coming out to be 17.56 at an angle of 10.89 degree amperes. But उसमें हमने क्या किया था? We had a delta connected unbalanced load. We transformed that into equivalent Y connected unbalanced load, found neutral to neutral voltage, and then used the equation like IA equal to VAN minus VNN by ZA. यहाँ हमें न्यूट्रल वो ट्रांसफॉर्मेशन की ज़रूरत ही नहीं पड़ी, और हमें न्यूट्रल टू न्यूट्रल वोल्टेज भी नहीं निकालना पड़ा क्योंकि हमने डेल्टा को वाई में ट्रांसफॉर्म ही नहीं किया। वी यूज दिस इक्वेशन IA इक्वल टू दिस। ये भी थोड़ी देर पहले हमने डिराइव किया, और इसमें हमें YLAB चाहिए था, YLCA चाहिए था। A ऑपरेटर से A स्क्वायर ऑपरेटर है -1/2 माइनस J√3/2। A operator है -1/2 plus J√3/2, because A square is 1 at an angle of -120 degrees, that is cos -120 degrees plus J sin -120, that comes out to be -1/2 minus J√3/2। और operator A क्या है? A is 1 at an angle of +120 degrees, that is cos 120 degrees plus J sin 120 degrees। cos 120 degrees is -1/2, sin 120 degrees plus J√3/2। ये ऑपरेटर ऑलरेडी हमने सिमेट्रिकल कंपोनेंट्स में डिफाइन किए। सो पुट देम हियर। YLAB भी थोड़ी देर पहले आपने निकाला, एंड ऑपरेटर इज दिस। सिमिलरली यू कैन फाइंड IB एंड यू कैन फाइंड IC। व्हाट इज IB? IB आपकी यह आएगी 1/90 टाइम्स -1/2 माइनस J√3/2 minus -1/2 plus J√3/2 minus 1/30 into 1 minus -1/2 minus J√3/2 into V, and this IB comes out to be 0.06933 V at an angle of -136.1 degrees. इसको जब आप सॉल्व करोगे, V is 0.06933 into V is 230 volts at an angle of -136.1 degrees. So that will give you IB equal to 15.94 at an angle of -136.191 degrees. 91 degrees amps. So this is same value which few moments back we have found. Similarly, you can find line current IC. Formula आपके पास है 1/60 times A square, A -1/2 plus J√3/2 minus 1/90 times A square, which is -1/2 minus J√3/2 minus A 1/2 plus J√3/2 whole multiplied by V. इसको जब आप सॉल्व करेंगे ये आएगा 0.04194 V at an angle of 126.58 degrees. V is 230 volts, so that means multiply by 230 volts. जब आप इसको multiply करेंगे, IC will come out to be 9.64 at an angle of 126.58 degrees amps. So this is line current IC without finding, hence we have found the line currents without finding the neutral to neutral voltage, without transforming the delta connected unbalanced load into equivalent star connected unbalanced load, and without finding neutral to neutral voltage using the operators A and A square. So this is another way of solving a three-phase unbalanced delta connected load. So in today's lecture we have solved three-phase unbalanced systems. First we took three-phase unbalanced star connected load or Y connected load, and we developed some equations. We used mesh current analysis, and using the mesh current analysis we found mathematical expressions for line currents IA, IB, IC in terms of phase to neutral voltages VAN, VBN, VCN, and the load impedances ZA, ZB, ZC. Various equations, 3 equations were found for IA, IB, and IC. And we then found IA, IB, IC also in terms of neutral to neutral voltages, like IA is equal to VAN minus VNN by ZA, IB is equal to VBN minus VNN by ZB, and IC is equal to VCN minus VNN by ZC. You know, VN, VBN, VCN, and ZA, ZB, ZC is given to us. The only unknown was neutral to neutral voltage. And we developed a mathematical expression for neutral to neutral voltage, which is ZA, ZB, ZC divided by ZA, ZB plus ZB, ZC plus ZC, ZA whole multiplied by VAN by ZA plus VBN by ZB plus VCN by ZC. Once you find the neutral to neutral voltage, substitute in previous equations, you get line currents. And based on that, we had some inferences. First inference was that if the system is balanced, supply is balanced, load impedances are also balanced, then neutral to neutral voltage will be 0. Second inference was if supply is balanced but load impedances are unbalanced, then neutral to neutral voltage will not be 0. You know, same equation you can use. Third was if supply is unbalanced but loads are balanced, then neutral to neutral voltage is 1 by 3 times VAN plus VBN plus VCN, and that is also not equal to 0 because the supply is unbalanced, source is unbalanced. That is equal to 1 by 3 times 0 sequence voltage. And fourth inference was that if both source voltages are unbalanced and load impedances are also unbalanced, then the entire equation has to be used for finding neutral to neutral voltage, because neutral to neutral voltage is not 0. Another inference was that if the system is three-phase, three-wire system, neutral wire is not provided, then VNN is not equal to 0, but phasor sum of 3 line currents IA plus IB plus IC is 0. And last inference was that if it is a three-phase, four-wire system, then whether your system is balanced or unbalanced, neutral to neutral voltage VNN is equal to 0, but the phasor sum of 3 line currents IA plus IB plus IC is not 0, that is equal to neutral current IN, and that is of course equal to 0 sequence current. Then we took a numerical problem and solved that numerical problem. In fact, later on we took a delta connected unbalanced load and solved it. How did we solve it? We transformed it into equivalent Y connected load and found the new equations for neutral to neutral voltage, and solved it same way, and we solved a numerical example based on that. And then I told you that if you don't want to transform a delta connected unbalanced load into equivalent star connected unbalanced load, and you don't want to find neutral to neutral voltages, then another alternate approach was used. We found the line currents IA, IB, IC in terms of phase voltages, and also in terms of line admittances YLAB, YLBC and YLCA, and also in terms of operators A and A square, which we have discussed while discussing the symmetrical components. So this is how you can solve an unbalanced three-phase Y-connected load and an unbalanced three-phase delta-connected load. So I will end my today's lecture here. So please go through this lecture. Try to solve these unbalanced systems, Y-connected and delta-connected yourself. take numerical problems, solve your solution of numerical problems will make ideas and concepts very much clear. Inshallah, in our next lecture, we will now take these three-phase unbalanced systems and we will try to compensate them using various types of compensation techniques. I wish all the best to you. Thank you.